Hi everyone, my name is Pierre-Hugues. I'm a senior IT consultant and the author on Java support patterns. Today's tutorial will provide you basically a thread analysis tutorial for the IBM JVM. What you will see is that the IBM JVM thread format or Java core is quite different than the Hotspot, and I'm going to show you via a case study how you can do a thread analysis. So I hope you will enjoy this tutorial for today.
So what you see here is basically a generated thread dump from a production environment following a stock thread problem on an Oracle service bus. So as you can see, it's the raw data. Typically you will get a Java core when you hit or you generate with the kill -3 option. That's a typical way to generate a thread dump if your environment is running on a Unix based OS, right? So this is the file you will get. And as you can see, the IBM JVM will generate it's called Java core file. That file generated and contains a lot of crucial details. So that's what we're going to go through today. I'm going to show you how you can do the analysis. It's very crucial analysis. As you will see, I'm not using any fancy tool to do that. There are a few tools out there like TDA and a few others. But I really recommend that you learn how to basically analyze the raw data. And after that, you can explore some other tools. But bottom line, start to understand the raw data, and at some point with experience you will be able to figure the issue fairly quickly. So the Java core, as you can see, it's kind of it's more than a thread dump, right? It's basically kind of a specialized core of the Java VM process. It contains a lot of information. So as I mentioned, in this problem we're seeing a lot of hugging threads and stock thread from WebLogic. So we went under production, generated kill -3, which is why you see dump event user here. That file was generated. Then if we go through, you will see it provides some of the detail, right? Like the OS version, some of the processor detail. You will see this is in the dump. Then you will see it provides also some detail on your runtime Java environment. As you can see, obviously we're using the IBM JVM 1.6 for this production environment. And some of the arguments, I did remove some for security purposes, but just to let you know that basically for this environment we're using 64-bit IBM JVM with 4 gig Java heap space. As you can see, Verbal GC was enabled, so we can track down the garbage collection health. And the environment was using the JC policy GenCon, which is a generational concurrent JC policy. And the xdump policy means that you basically can generate some heap dump of the process. Now, this is just basic information in the header of the Java core. You will see later where the true thread dump is. So again, when you get that file, you don't really care about this information for now. It's more reference information. You have also some of the user limit detail on the process level. This is sometimes useful from let's say a socket perspective. And then you also get detail about the actual JVM and the heap, right? So you know, for example, how much free heap basically at the time you took the snapshot. You will see how free heap you had versus the total capacity. Then you also have access to all the different native segments as well. Again, the information is available. It always depends on your problem context. In the context of a stock thread problem, you only really need that level of details. But it's always useful to understand what was the availability of the heap space at that time. So let me jump to the logs portion, right? So you will see in the thread dump there is a log portion, and just above that, if I scroll back up a little bit, you will see you get also a JC history. So you see the Java core of the IBM is pretty good, right? It's contains a JC history as well, detail on the heap. So it's very important when you try to correlate stock thread problem with excessive JC. So this is always a good idea to look at this data unless you know exactly what's going on with your stock threads there, right? So in our case, as I said, we saw some stock threads, so don't spend too much time on this. Just scroll down quickly. The next step is the log subroutine. The log subroutine in Java core, that one is a really crucial section of the thread dump, right? So it contains all the different dependencies of the thread. So for example, if you're dealing with thread log contention, right? or thread lock chain, then that will show up in the lock subcomponent dump routine. As we can see here, you can see, right? So the way it works is that you will see chain of threads. For example, you will see typically like this, right? You will see one thread, like in this example, we can see thread 16, which did acquire flat locked, right, on this object. And all these guys are waiting, right? You can see these are all stuck thread from WebLogic. All these are waiting to acquire the flat lock on this object, which is held by thread 16. So you see, this is just an example, right? So which is why, and this is a big problem for us in our case, right? So right away, by looking at a lock routine, we know we have a big problem here. We have a lot of threads, about 200 threads here waiting from a single thread to complete its processing so it can release a flat lock. And for your reference, a flat lock means synchronized block of in the code, right? So for example, if you write Java code and you put synchronize statement, that will basically translate the flat lock. When the thread goes in the synchronize, it will basically hold a flat lock on the object monitor. And then if, for example, if your computing task is taking too much time, then this will generate a waiting queue like this, okay? So let's keep this one in mind for now. And let's go to the thread dump. So when you start looking at thread dump, it's always best to start at this portion, right? So don't spend too much time going through the lock subroutine at the above. The locks subroutine that we just saw will serve you as a reference. So when you get a thread dump, always start with this, right? So search for the word threads, right, at the beginning, right? Just need to go back, do a quick search. Don't spend too much time, you see, and just search after the JC and quickly move to the thread subcomponent. This is your actual thread dump information, and then depending what you will find a thread dump, what you will learn, then you can go back in the reference, which is the log subroutine, and the heap history as a reference or supporting data, right? So always start to analyze this portion right here. So back to our problem. So basically it's giving us all the detail of each active thread and the JVM at a given time. Again, a common mistake I've seen when people start to learn how to analyze thread time is to go on to each thread line by line and try to figure out. Well, obviously it's a common reflex if you're quite new to this, but my recommendation to you is no, don't do that. Start with a fast scan of all the threads and try to pinpoint a pattern or 2 or 3 patterns. You see, this is how you have to analyze this stuff, is to try to pinpoint patterns really quickly. And for that you need to be able to differentiate a healthy thread versus a non-healthy thread, right? Healthy thread will mean thread waiting to do something, and a non-healthy thread means it's a thread doing an actual computing task, but it's hanging or waiting to either a IO call or it's waiting to acquire a flat lock, like in this case, like you will see. So if we have a look at this, right, thread detail, this is the anonymous native thread. This we don't care too much here. Here the next thread in the chain, you see it's time event generator, kind of an internal thread. You see it's in wait state, nothing to worry about. From WebLogic perspective, typically you will see, especially for you know, earlier version or later version like version 9 plus, you will always see like this, right? So the thread name is created with WebLogic default self-tuning. So these are the threads that you have to worry about. The other internal threads, unless you see some CPU issues, you don't have to worry too much. So here's our for example. You see, execute thread 8 from the queue default self-tuning. It's the main queue of WebLogic, right? So all thread will be basically defaulting to that queue by default. So the way it works, you will get this, right? You will get the state of the thread in the WebLogic term, because WebLogic has its own status of the thread. So you always see that here. So status of the thread, obviously it's stuck. So we know this thread is stuck. Stuck means by default it's taking more than 2 minutes to complete its work. Then you will get the ID of the thread, execute thread 8. Then you get the name of the queue. As I said, that's typically what you will see for WebLogic. Then if you start scrolling on the right side, then you get some native information about the thread, including the native state, which is B, which means blocked. Okay, but don't worry too much about this state. I've seen scenarios where the state is healthy, but the actual thread is stuck as well. So it's not, so don't worry too much about the native state. Worry more about the actual computing task it's doing here, right? The more important thing in analysis is the stack trace, the Java call stack. Okay, so the IBM VM will give you two things, the Java call stack and the native call stack. Native means the actual portion of code that goes beyond the Java call, right? JVM, native code execution. Again, don't worry too much about the native, so don't start to spend too much time analyzing that. Your core of the work should be on the Java call stack. This is where 95% plus of the issue will arise, and this is where you have to focus your time on. So as I said, start quickly, go through that, look at this thread. Oh, so we know this thread is stuck. Now you start looking at what this thread is doing. The core of your work is analyze the stack trace. If you did have a look at my tutorial on my blog, you will see that when we talked about the stack trace, it's very important that you analyze from bottom up, right? A Java stack trace is like an exception that you would see in the log. It's the execution stack, right, of the thread. Either if it's triggering an exception, in this case it's an execution snapshot of what that thread is doing at that time. So always start from bottom up. So in this case, what we can see is, well, an execute thread was fired on WebLogic, and we can see it's executing its work. And the cool stuff about the stack trace analysis is that you will be able to understand the type of request. You see? Then we can see the request, it's execute JMS session. So we already know right here that this request, it's not an HTTP call. It's right at a JMS. It's basically trigger from a JMS call. And then we can see there's an MDB fired, right? And then we can see there's some internal code executed here, right? And then there is some again, this is the OSB product, right? So it's a big abstraction layer. It will be more friendly with your application code. You will be able to see your application code, but for the OSB product, you have to go through all these abstraction layers, right? And then what it's telling us is that it's trying to execute a kind of a callback from one of the call internally to OSB, right? And then basically what it tries to do after that, execute some other pieces of code trying to basically begin a transaction, and then that thread is stuck at this line, right? So question is, where is it stuck, right? Well, what you have to understand is that for IBM VM, when you see something like this, the hotspot thread dump will actually show you, for example, waiting to lock, right? In this IBM VM, what I don't like is that you don't see that here, right? So when you see a line like this, you have to think that that thread is probably waiting to acquire a lock. And in order to prove that, especially if you know that the native state is blocked, right? Then what you do, just to confirm, right? You just search the execute thread, right? You can go back in the lock subroutine, right? Oh, there it is. Here's our guy. See that? So which is why the lock routine is very good as a reference, showing you basically the all the synchronized. So we know that this thread, based on the stack thread that we saw at that line, it's waiting to acquire a lock on this guy. So that's good. So we already know that thread, we know what it's doing, we know it's waiting to acquire a flat lock. So we can, we can go back now to the thread section and move on with our analysis, right? So now that you know, at some point we'll be able to see if other threads are waiting, right? Then you continue analysis. You move to the next thread. This one is called dynamic SSL. This one we don't care. It's more for the SSL inbound request. Then you continue. There's another thread, right? So again, as I said, you have to move quickly, right? You don't want to spend like 2 days on this, right? So you have to move and then try to figure out a pattern fairly quickly. Now you move on. You see? Then this thread, what it does, again, this thread is stuck, right? State is blocked again. Now Java callback, as I said, bottom up, right? Oh, this one you see it's an HTTP call. Again, it's a service bus, so typically it's web service driven, so it's executing some web service call right here. And then again, in the same code, we can see BA, WLI, derive cache. This is kind of a object in USB used for the service definition, let's say proxy and business service definition. So that code is heavily solicited, and we can what this code is showing us is that there is some synchronized piece of code in there, right? And we can see this thread is also stuck and very likely also waiting to acquire a lock on an object monitor. Again, you can do the same analysis, right? You search, you go back up, and there you go. You will see again from the lock subroutine 83, it's part of this, right? That same chain. So bottom line, in this case, you can see we have so many threads that very quickly after a few minutes you will realize, well, I definitely have a pattern. So you can go back, you search this time down, go back to the thread, right? So at this point it's quite easy, right? You search up and down using the thread ID, and you're able to quickly navigate through the thread dump just looking at the raw data. Then at this point, when you see 2 or 3 threads in the same pattern, then move more quickly. Then you know this one is in the same condition. No point to spend too much time. You see, these are what I call healthy thread. You see some of the thread, they are not doing anything. Then you can move quickly, right? This one again, not too interesting. And then you can see again, execute thread throw 7, same piece of code. You see, transaction manager begin. Also, this one, this is where it gets interesting, right? Because this thread is in active state, but it's in block state. So you have to be careful not to get confused. So, because WebLogic has its own state. Active means WebLogic has no idea at this point if this thread is healthy or not. So you have to do your own due diligence, because the state will change to stock only when you reach your stock time configured in WebLogic, which by default is around 2 or 3 minutes. But it's still possible that this thread is waiting to occur the same lock, even though it did not reach that 2 or 3 minutes buffer at this point. So you think it's healthy, but this thread is not at all. It's waiting in the same condition, right? And we can see it's blocked. State blocked means it's waiting to typically acquire some locks. So if we surge back down just to validate our assumption, you go back there you go. You see 307. You go back up, and this guy is part of our big chain again. So at some point you can see there's no point spending too much time. You see all these guys, we can see they're all waiting to acquire a lock. Now that we know that all these threads are waiting to acquire a lock, the next step is what? Well, you have to analyze which thread is holding this lock, right? As a next step. So we go back up to the chain. So this time, the next part of your analysis will be to look at the culprit. So we know that all these guys are waiting to acquire a flat lock or synchronize, right? On an object monitor, which is transaction manager. It's internal to the product. So it's not Java source you have in your end, obviously. But then we know which thread is the culprit, right? So then we know it's thread 16. So what's the next step? Well, we need to understand what the thread 16 is doing. And here's thread 16. So you surge back down, look at thread 16. And what is the thread 16 doing? Well, you see this one is in basically park state. This is where it gets a bit complex, and I'll explain this whole issue after. But then the idea is to identify the culprit, because in this case we have a stuck thread due to one culprit thread, creating a thread lock contention chain, right? Basically a multiple thread waiting from only one thread to complete its work. So you have to see what this work is doing. So let's analyze again bottom up. So we know that thread is in run state. Run. Oh, look at this. WebLogic deploys service deployment callback. So what it's telling us is that this thread was fired by the WebLogic deployment service. It's a deployment receiver callback. So what it means is that there was some action taken in the console, in the WebLogic or service bus console. So for example, in OSB, when you take an action in service bus console, let's say you want to make some change to the logging from a proxy or business service, this action will trigger a thread from the managed server, we're basically trying to commit that change to all the member of the cluster of that OSB, right? That's exactly what it's trying to do here. You see, it's receiving it, it's trying to commit the change. Let's say you want to increase logging level for one business service, so it's trying to commit the change. We can see it here, you see. So far so good, right? Now it's trying to end the transaction, just the deploy commit, right? It's kind of a transaction on this process. It's trying to commit, but then you see it's trying to run through this code, and it's trying basically to, here, this is where it's getting a bit tricky, because it's trying to acquire a write lock. I'm not, if people aren't familiar with the reenter and read write log, this subject will be out of scope for today. But it's basically another way for you to implement Java concurrency. So instead of just implementing flat log via synchronize, you can also implement your thread safe code, your non-thread safe code, I mean, by using a reenter and read or write log. So it kind of allowed you, for example, you can, for example, acquire a read log, and multiple thread could be acquiring between each other some read lock. But obviously, if there is a thread attempting to acquire a write lock, then there are some rules that apply. Obviously, that the read lock has to be released, and obviously same apply for write lock. So this is different concept, but that's the way OSB code implemented that portion of the code, which is around the management of the service definition for your proxy and business service. So there is it's heavy duty code which is used. So it's kind of using a mix of synchronize but also reenter and lock. So what this thread is showing us is here is that this thread is attempting to acquire a write lock, and as we can see, acquire park and check for interrupt. That typically means that this thread, right, is unable to acquire the write lock on the object. And typically that will happen if another thread is holding either a read or a write lock. So this is where it's getting very interesting, right? Because we have a culprit thread which is holding up a flat lock, but that same culprit thread is waiting to acquire a write lock. You see that? Again, the IBM JVM will not show you, unfortunately, the native lock routine for the reenter, because this code is part of the JDK, so it's not basically detected by the lock subroutine. So you have to try to understand where you may find that. So at this point, we identify a culprit. We know it's a deployment callback, and I can give you, I know in this problem case, I know we had the administrator, we took an action in the OSB console, and by taking this action during heavy load, what happened is that the commit on our managed server did not work and did end up in this hang scenario, and ultimately triggering a domino effect. As you can see, all the threads waiting from this guy, right? And this guy unfortunately is stuck waiting to acquire a write lock, and I will show you the potential culprit soon, but at least that gives you an idea how you can analyze that data. Now what we did was basically to run some search through the derived cache, because this is kind of one of the culprit is a derived cache, and what we found is that in the derived cache there is definitely some piece of code basically that also did attempt to acquire some read lock, right? And at some point you end up, this is why you see in the thread 616, right? Because there is another thread which did acquired also a read lock on that same monitor. This will be presented as a part 2 of this analysis. So this part 1 was just about at least to give you an idea for the thread dump and how you can identify that chain. So as you can see, in summary, always start with the threads section, as I mentioned. Go quickly through the threads, identify the pattern, then go back to the lock subroutine, right, as we just saw, and identify the culprit, right? When there is a culprit, like in our case, and after that analyze the actual culprit itself and understand what its work is doing. And typically you'll be able to pinpoint, okay, yeah, this thread could be trying to acquire a connection from a database and so on. In this scenario, in this thread DOM analysis pattern, the pattern is thread lock contention or thread lock chain due to one culprit. And the part 2 will be showing you the actual deadlock condition. What you will see in the part 2 is that this thread is in deadlock with another thread because of a reentrant read-write lock. So there is a lock ordering problem here that will be presented as a part 2. So for now, keep that in mind, and I hope you have appreciated this video. I will be providing you a lot more videos going forward with several patterns. Obviously this is just one of the pattern, which is a thread lock chain. There are many patterns that you have to understand when you analyze thread DOM. So this is just the first video, and I hope you enjoy it. Please feel free to ask me any question or post any comments on this video. Thank you and have a good day.